Today what we're going to do is we're just going to take a few minutes and finish up the mass spec slides. And all we're really going to do is look at several different ways to separate the ions once they're formed. All right, so what we've done, when we have talked mostly on mass spec, we've talked mostly about spectra that were generated using electron impact ionization. So the Friday before spring break, we talked about some other ionization methods, and any of those ionization methods can be paired with different ways to then separate to be able to analyze the actual ions that are formed. Okay? I showed you at the beginning one method which was called a magnetic sector instrument. Okay, and I've got a diagram of that again, and what we've looked at so far was the single focusing magnetic sector instrument. And basically we shoot the ions down a tube, it goes through this magnetic field and it causes it to curve, and the amount of curve depends upon the mass to charge ratio. We can also stack up more than one of these sectors. So a common one is the double focusing instrument, and this is oftentimes used for high resolution mass spectrometry. And then there's other methods called the quadrupole, the ion trap, time of flight. I don't think I have a diagram for this Fourier transform one. Tandem mass spectrometry is essentially where you can hook together essentially more than one mass spectrometer. So you separate an ion, and then you can select one of those ions, and you give it a chance to fragment, oftentimes due to some kind of collisions, and then you follow those ions. And so that can be useful as well. So this is just another diagram of the single focusing mass spectrometer. And remember, what we wrote up last time was that if we take this curve here, we'd have some radius to the arc, and the radius of the curve was equal to the square root of 2v over b squared, so that's the magnetic field, times the mass to charge ratio. Okay, so we looked at the fact that as for a given voltage, which is the accelerator voltage coming out of the ion source, and the magnetic field, different mass to charge ratios are going to curve at different amounts. And so if we have a higher mass to charge ratio, it's going to have a wider radius, right? The radius increases as the mass to charge ratio goes, and so at a given magnetic field and voltage, essentially only one mass to charge ratio will make it all the way through these collector slits into the detector. All right, a higher mass to charge ratio might just hit the outside of the curve, right? A lower mass to charge ratio would curve too much and hit the inside of the curve. But if we scan through either the voltage or the magnetic field, we can essentially gradually, if we have it this way, we can kind of bend this whole curve and scan through all the different mass to charge ratios. Okay? And so that's the way we would essentially get, the full mass spectrum. So hook together more than one of these methods to separate the ions. And so this is called a double focusing instrument. So again, we have some way to put our sample in. We have the ionization source. And so this first part is all the same. We have the voltage accelerator plates. We send it down, and this one has a magnetic sector here, which is like what we saw in the last one. but it comes out of the magnetic sector, it's kind of refocused, or we collect the ions and then it's refocused and then it's sent into what's called an electric sector. And so it just has a voltage across here that can also cause the ions to curve. So we do it a second time, goes through a second collection slit, and then gets detected. And so because we're refocusing in the middle and doing this a second time, this creates a very high resolution instrument. So this is one of the instruments that they use for high resolution. All right, there are some instruments though. This is a diagram of what's called a quadrupole mass spectrometer. And so the way that this works, it essentially has these 4 rods, or poles, quadrupole. The ion source is over here. The ions are accelerated through this tube and down between these different poles. And so the poles can have voltages placed across them, and both direct current or alternating current. So you might think about here it has a plus, plus and minus. So if you have a cation going down here, it's going to be attracted more towards the minuses and repulsed by the plus. But as it starts going towards the minus, if these charges switch, and this now becomes plus, then it'll be deflected off of that and go towards the minus, and then if it switches again, and so how the strength of the charges and how fast they alternate, they can send the ions all the way down through this quadrupole. Okay? And I think based upon the charges and the rate, they can select or scan through the different mass to charge ratios as well. Okay, so these are usually much smaller instruments than those big ones, less expensive, oftentimes hooked up to a gas chromatograph or something like that. But these are usually the lower resolution types of instruments. So this is the ion source here. Okay, I know these are kind of brief. It's more like just naming them and showing a picture. I'm not really an expert on this stuff. And there are some descriptions in our text on this as well. The next instrument is called the ion trap. All right, and this is kind of an extension of the quadrupole. This one, so here's the ion source, or ion volume, the ion source down here at this end. This one has essentially 3 different electrodes. This one here, which is actually a ring. Okay, so this is just a cut through it. It's like a donut. And then this is an electrode here, and there's one on this side as well. So there's the kind of the donut in the middle, and there's the 2 electrodes, the caps on each end. And they can run various experiments with this by either having a direct current or alternating currents on the trap ring electrode versus the ends. So essentially the ions come down here in the middle and they get trapped in here and they can be cycled inside the ion trap. And so our text talks about some different experiments and how they would change the voltages across these different electrodes. They can run experiments that are essentially look like our normal mass spec results. They can do experiments where they can set essentially a high and a low cutoffs for mass to charge ratio, and they can even make those very narrow so they could select essentially a single ion and just monitor that single ion. And in fact, in a single instrument, they can select ions. They can then add some energy to those ions and cause them to do second fragmentation based upon collisions between them. So they can do this whole mass spec, tandem mass spec experiments in the same instrument. So whereas I think these started out to be kind of a cheap, low technology method, now there's lots of different applications to them. But again, a lot of them are not that big, too. They're not real huge. So these have a lot of applications. Dr. Brown is what's called time-of-flight instruments. And time-of-flight is kind of a simple concept. And essentially the ions are accelerated, and as long as they're all accelerated with the same energy, the time that it takes for them to fly down, and in this instrument it has this reflector plate that they're curved away from, the time that it takes is determined by their mass to charge ratio. So the time equals the square root of L2, which is the length. It's probably the length of the path past the reflector and back to the detector, times the mass to charge ratio over 1 over 2 EV. I think EV is electron volts. It must be the energy at the acceleration. And so this is sometimes good for very large molecules.
What's a large molecule?
Like proteins and things like that. Usually it's paired up with some type of laser desorption technique, like because oftentimes it's MALDI, matrix-assisted laser desorption, because they need to be able to ionize all of the molecules at the same time with the same energy. Because if their energies are different, then they'll accelerate differently, right? They all need to behave the same. So this is just another method, a table of some of these methods that kind of say some of the pros and cons and their ranges. So the magnetic sector, which all of the spectra that we looked at before probably came from, talks about the mass range, the resolution. So this has quite a high resolution, right? We need to be able to go to something like 0.0001 to do high resolution mass spectrometry. So advantages, high resolution. Disadvantages are that it's, has a low sensitivity as far as mass spectrometry goes. But I think mass spectrometry is more sensitive than a lot of other techniques that we use. Expensive, and you need to know a lot to run these things. The quadrupole doesn't have quite the mass range, and only unit resolution, so it's more of a low resolution instrument, but it's inexpensive, easy to use. These are more the benchtop ones that with a GC or something attached. You don't need to be an expert to maintain it. Disadvantages: low resolution, low mass range. Okay, the ion trap, same mass range, but it can, this says also just unit resolution, but again, inexpensive, easy to use, that kind of thing. Look at time of flight, it says an unlimited mass range, high resolution, high sensitivity. And then the Fourier transform is interesting because essentially they make the ions and then they put it into essentially a superconducting magnet, like an NMR magnet, and they can just cycle the ions within this magnetic field, and so they can get very high resolution, but it's very expensive too. So I think, the most common are probably the top three. When you just send your sample in for a low resolution spectrum, they're probably they might be using just the magnetic sector. Those seem to be kind of the workhorse instruments, or quadrupole. I think those are the most common.
But on magnetic sector, we can get a high resolution.
Yes. Usually it's that double sector one for high resolution, though.
Oh, okay.
Yeah. But, those instruments, would be, they take up like a couple of tables here, too. They're quite big. All right, so this is mostly just to recognize a few of the names of methods and stuff and see a diagram. All right? Okay, so that's the end of our mass spec part.
It's on
Okay.
page 13 too.
Oh yeah, there are some descriptions. They're reasonably brief in the book as well, but they say a little bit more than what I did.